Okay, with this video, I want to talk about computing some risk metrics using our fragility and vulnerability functions. And specifically, we'll look at these three metrics. So we want to look at the annual rate of failure being some discrete binary outcome. We're going to look at a loss exceedance curve, and we'll look at average annual loss. So all three of these metrics are going to combine our consequence models with our ground motion hazard models to get to an aggregate metric of how much risk we're facing in a given situation. All right, so let's look at failure rate first. Here we're going to combine a fragility function with a ground motion hazard curve. And so when we're using fragility function, just as a reminder, those fragility functions are describing binary outcomes, right? So it could be collapse of a building or occurrence of minor damage or worse or something like that. And the idea is we're going to get to the rate of failure. So how often per year do we expect to see a failure? And we're going to get there by thinking about the probability of failure given an intensity measure. So that's our fragility function. And so we're conditioning on IM equals X. So we also need to know what's the rate of IM equals X. And then we'll integrate up with dx. So this is like a total probability theorem calculation again, but with rates. Hey, notably, this is an equals though. Our typical ground motion hazard curve is the rate of exceedance of X. And so now we need rate of occurrence of X to do this conditioning calculation. Okay? So the way that we commonly do this is we're using the second equation. So this is the most typical way you'll see this written out. And inside of this kind of term here on the right, we've got the hazard curve. So the rate of IM greater than X is our hazard curve. What we'll do is we'll take a derivative of that hazard curve with respect to X. That'll give us, it's like taking the derivative of a CDF to get a PDF. We've got derivative of exceedance functions, which have negative slopes. So we actually need the negative of this thing. And so to get to the negative, we typically put an absolute value around that derivative, which will flip it to a positive value. And then we'll integrate by dx. So that's a common way to write that. Let's talk a little bit more about this derivative. It's similar to the occurrence rates for magnitudes versus exceedance rates for magnitudes that we handled up in chapter 3. But let's add a few notes just because this is a tricky thing here. The way we can write this is the derivative, just as a definition. The derivative of hazard curve is going to be this term over on the right. So in parentheses is going to be the limit as dx goes to 0 of this finite difference. Right? So we'll take the exceedance rate of IM above X plus dx minus the exceedance rate of IM exceeding X, and we'll divide by dx. Right? So there's a plot of a typical ground motion hazard curve. We've got intensity in terms of X on the X-axis, and then exceedance rates on the Y-axis. And what we're doing here when we're taking the derivative is we're going to take this hazard curve at some point X, and at some point X plus dx, and we're going to take those two values. That's the numerator. Right? So the hazard curve value at X plus dx is the first term. Hazard curve value at X is the second term. We'll take the difference between those two. You can note from the figure that this first term is smaller than the second term. It's lower in y-axis value, so that'll be a negative number in the numerator, but the absolute value will make it positive. And then we're going to divide by dx, so that's going to turn this into a slope. All right, so we've got a kind of a rise over run calculation. And then we're going to let dx go to 0 to compute this derivative. The other thing we could do in the second line here, what I'm noting is if we drop the dx's from the denominators of both sides, we could say that it's a little funny looking because we've got just d lambda IM greater than X here. And we can note that the difference in the numerator is just the rate of seeing IM values between X and X plus dx. And so because we're going to use this derivative in numerical integration, we're often just discretizing this thing anyways. And so we could just write, well, this right-hand side is the difference between these two exceedance rates. And I flipped the order of the exceedance rate. So now it's IM greater than XI minus IM greater than XI plus 1, which is the X plus dx. Then we don't need an absolute value because that'll be a positive. So in the figure over on the right, we could denote with this XI and XI plus 1 that this could be XI and XI plus 1. And we could do this for kind of a set of other X values as well. And then just to denote that this is now a kind of a discrete difference, we could call that delta lambda I. So it's the change in rates as we step up in an IM value. And then we could indicate the subscript I to kind of indicate where we are in this thing. Okay? So this whole thing here is analogous to our magnitude exceedance rates, where we're trying to get these kind of occurrence rates times a delta M. Okay, so with that setup, and particularly with the discretization, we can think about our general form of this failure rate up top. If we discretize to solve this thing numerically, we've got it rewritten here where we're going to do a summation. We've got a discretized set of IM values, and we've got discretized rates of occurrence. We'll just put those things together and add them up. That's a kind of numerical integration. Okay, so to think through what the math looks like here, we can think about what if we had a ground motion hazard curve, and I'll grab one of the hazard curve sets of data from earlier calculations in the hazard sections. So let's say we've got a hazard curve. That's the kind of line number 1 on the plot over here on the right. And we have a fragility function, and that'll be a log normal fragility function with the given theta and beta, and we know how to use those. That'll be plot number 2 over on the right. Okay, and now we want to know what's the annual rate of failure. Let's do some calculations to get to this annual rate of failure. What we'll do is I've got in the left column here a discretized set of xi. So we're going to start from very small xi's, and then once I get up a little bigger, I'll just discretize in units of 0.1. We've got our hazard curve, and we can get this numerically from whatever source we're interested in or from prior hazard calculations. And we've got our fragility function, and we can do that by evaluating that log normal CDF, using the xi's in the first column, and using the theta and beta that were given for the problem statement. And then what we need is that discretized hazard curve derivative, this delta lambda I. And we'll take the differences between the exceedance rates at adjacent xi levels. So we'll take those in the top row, we'll take 0.0252 minus 0.00585. And then we'll step through these moving down. Visually what's going on here is we're taking those derivatives just like we had spoken of earlier. So if I've got xi and xi plus 1, we'll take the hazard curve value there, and the difference between those two, so the height of the step here, that's delta lambda I. Okay, so that's what's getting computed in that middle row. So we've got the product of the delta lambda I in the third column times the fragility function in the fourth column. That gives us the fifth column, this product. We can see at the very low levels of xi, the fragility function says there's 0 probability of failure. So we didn't need to include those, but we could go down low just to make sure that there's no kind of contributions there. Then the fragility function is going to go up and up, heading towards 1. The occurrence rates are going to go down, so stronger ground motion intensities get less likely. But the products anyways are over here on the right. And then we'll take the sum down at the bottom. That's the summation for that failure rate calculation. So we see for this hazard curve and this fragility function, we've got about a 5 times 10 to the minus 5 annual rate of failure. One thing that's maybe interesting to look at as well is the contributions to the failure rates. So we can see numerically, I've got small contributions up in the top few rows. Then we're up into 10 to the minus 6 contributions, and the numbers get big at 0.4 and 0.5, and then they start heading back down. If I just plot those values in a bar chart, that's the next slide. They look like this. So these are the numbers that we added up to get to the overall failure rate. And so we can see here the contributions of kind of which SA values were contributing the most to the overall failure rate. And I think SA is our metric that I was taking some of these numbers from. Okay, so we can see we got this big peak at 0.4, 0.5, 0.6 G. And if we go back to our earlier figure, that could make sense that this is this middle ground here where the two curves are both kind of non-zero and non-trivially non-zero. So the ground motions are occurring frequently enough that they're important, and the failure probabilities are not zero anymore so that they contribute a lot. As we head more towards the right, the failure probabilities go up pretty high, so it's pretty likely we'll get a failure. But the ground motion hazard is saying that the rates are pretty small. And looking at the table, at say like 1G, we've got a very high probability of failure if we see it, but we've got low occurrence rates of those strong ground motion intensities. And so they're actually not contributing too much relative to those lower ground motion intensities. And that's a pretty common pattern that when we look at the fragility function, oftentimes it's like the 10 or 20% failure probabilities. that are contributing a lot, because it's possible that the structure could fail, and those ground motions are just so much more likely in a relative sense that they give us this big peak. The other thing that's maybe notable on this figure is this big bar at the right over at 1.5 G. And so that looks like an outlier. So what's going on here? What I've done is, it's because we cut off the table here at 1.5 G. So effectively, there's one more row that's not shown that says xi is equal to infinity. The exceedance rate is 0. And then when we compute the difference in hazard curve rates to get to the occurrence rate, the whole remainder of the hazard curve is all going to 1.5 G. We could have discretized out further and had a 1.6 G and a 1.7 G and so on, each with their own occurrence rates. But what we've done is effectively stacked all of that into 1.5 G. And so we get this one big bar here. And that's fine because the 1.5, 1.6, 1.7 G, they all would have had a failure probability of 1.0, right? I've already gotten up to 1.0 at 1.5 G. And so 1.6, 1.7, 1.8 G, they're all going to look the same in terms of the structure's perspective. So why not just group that all into one bar here? So in terms of this plot, it's a little bit of a numerical artifact, but I like to show that and talk about it just to think through what exactly is going on with our calculations here. Okay, so that's failure rates. Next calculation to talk about is what we call a loss exceedance curve. Sometimes the vertical axis will be probabilities of exceedance. In the insurance world, that's reasonably common, and it gets called an exceedance probability curve or an EP curve. So EP curve is a very similar calculation to this, but just using probabilities instead of rates. So in this case, rather than combining the ground motion hazard with a fragility function, we're going to combine it with a vulnerability function that's giving us consequence exceedances. Okay, and then over on the right, we've got that same kind of derivative of the ground motion hazard curve and the same discretized form. So the difference here is, instead of a probability of failure, we've got a probability of consequence exceedance. But those are still going to be probabilities, so numerically the calculation is going to go very similar. Just to visually sketch this one out, let me draw some pictures. So we'll start with the ground motion hazard curve. So we've got the kind of the exceedance rates, and we'll discretize the x's into xi's, and then we'll take the differences between those as the lambda xi's. Okay, so those are the delta lambda i's. Then we'll have our consequence function. Got a median uncertainty. Okay, so that's our consequence function. And what we're going to do is we're going to pick some consequence level that we're interested in. C. And then at each x intensity we're interested in, what's the probability of exceeding that consequence. Right? So that's going to be the shaded areas in these consequence functions distributions, just to visualize it. We can compute that out of our functions as well. If I just think about these shaded areas mapping down into some points on this probability space, then we can get this function filled in. And in some sense, that's like a fragility function at this point. You either had an exceedance or we didn't. But those are the numbers that we're going to plug in to this probability of exceedance curve here. Okay? So if we put those two together, we get a rate of exceeding that level small c. If we change small c, we're going to get new probabilities in that blue function at the bottom of the screen, and we'll get some new calculations. Okay? And if we do that a bunch of times, we'll get a set of points for exceedance rates of c. And that's what this plot on the previous slide looks like. The sketch on the previous slide was first kind of one level of small c, and we get one exceedance rate. As we go to different consequence levels, we'll get a different x-axis value, and we'll compute a different y-axis value, connect them together into a curve, and we've got our loss exceedance curve. That's the idea there. Okay, last metric is average annual loss. So here the idea is we're going to compute what's the expected value of the consequence metric per year. And so AAL is the common acronym, and so loss is the number that gets put there. A lot of times that's economic loss when this is used. So I'll try to connect this to the more general consequence metric, but loss is the number, or the word that gets used in this metric very frequently. Okay, so the idea here is we're going to take the same discretized rates of occurrence of the ground motion hazard curve, the delta lambda I. That's telling us how often we see those different levels of IM equaling xi. And then we're going to multiply that by the expected consequence given IM equals xi. All right, and that was a previous calculation that we had in the earlier videos. Okay, we add those two up and we get the expected consequence. Because the delta lambda I is in units of per year, this is the expected consequence per year. Right? So that's the typical way we compute this. Interestingly, it can also be computed by taking that loss exceedance curve, our previous metric, the lambda c greater than c. If we just integrate that for all values of c, that will also give us the expected value of the consequence. It's not intuitive why that would be the case, but there is a derivation in the textbook. If you want to see that derivation, that's equation 9.35 in the book. You don't need to know how to derive it or anything like that, but I'll point you towards that reference if you're curious. Okay, so thinking through computing this average annual loss, we can do a real simple one here. So on the left-hand side, I'll do a quick and dirty case where there's, just to simplify, let's consider that there's only 3 possible PGA values, 0.1, 0.2, 0.3. We've got a hazard curve here, the 0.06, 0.016, 0.003. That's back from the chapter 1 example if you're interested in. Implicitly, there's a PGA of infinity with a 0 exceedance rate as well. And then we've got an expected consequence. So these are just some made up numbers, the 100, 400, and 1,000, given those different PGA levels. So if we want to do our calculation, first we're going to need that delta lambda I. And we're just going to take differences here between the exceedance rates. That first one is 0.06 divided by 0.016. So equals 0.044. Next one, 0.016 minus 0.003. That's 0.013. And then the last one is the 0.003 minus the 0. So we get the 0.003. All right, and we can always spot check that these delta lambda i's, it's easy to tell in this case since there's only 3 of them. If you add those all back up, we get 0.06, which is the exceedance rate of the lowest x value. So that consistency should maintain. Okay, so with the delta lambda i's, now we just take the expected consequence times the delta lambda i's to get our average annual loss. So the expected consequence. So for the PGA of 0.1, we got a consequence of 100 times an occurrence rate of 0.044. Similarly for the other terms, and then get 12.6 in whatever units of consequence that is. So I guess one thing we could note is that the expected consequence is a lot less than the consequence for even the smallest PGA level. Smallest consequence was 100 in the table. We've got a 12.6, and that's because even the smallest PGA level had an occurrence or an exceedance rate of 0.06 per year. So most years we're going to have nothing happen and no consequences. So the average consequence should be lower than the consequences associated with any of these. Okay, so that's a real simple case with just the 3 PGA levels. More realistically, when we do this, we're going to have kind of a continuous hazard curve, so we can discretize up those IM values more finely. And we're going to have a mean loss model. For instance, from that HAZAS calculation, we did the calculation earlier with loss ratios. We had 0.5 G peak ground acceleration gave us a mean loss ratio of 0.14. You could fill in a whole curve using that earlier data, and that mean loss ratio curve could be integrated with a ground motion hazard curve to get an average annual loss. So you just imagine a much longer table with more continuously varying PGA values. That's more typical, but hopefully this gives you a sense of the mechanics. All right, maybe one thought. So we've got these different metrics to the annual rate of failure. That's useful for calibrating things like safety of structures. If the failure is something that endangers safety, we could see is that occurring too frequently to be satisfactory. The loss exceedance curves, that way we can see how much money might we need to keep in the bank if we're anticipating occasional losses to our assets. Average annual loss, why is this useful? So average loss per year, or a very common way in which this one's getting used, is in insurance-related pricing. If I'm an insurance company and I'm selling an earthquake insurance policy for some building, I'd like to know on average how much loss there's going to be to that building so that I can make sure to price my insurance policy that I'm going to be, profitable, even if I'm paying out that much money on average. So that's a really common way to do this. Similarly, any other sorts of like financial transactions, knowing the losses per year can be really helpful. But the thing to keep in mind that's a limit is that it doesn't account for the range of outcomes that we might see. And we could think that through by going back to the previous slide. So my expected cost per year was 12.6, and you could imagine kind of $12.6 or something like that. I could say, okay, that's how much I'm going to have to cover per year in expected earthquake losses. But for any of the actual peak ground acceleration values in the table, the losses were a lot larger than that, right? And they could potentially be as large as $1,000. And if I'm not comprehending that $1,000 is possible, I'm just looking at this 12.6 number, I'm not seeing this kind of, sometimes we call it tail risk. And so that variability is important. That variability is also what's driving the insurance transactions. If the average losses are 12.6 say dollars per year, maybe an insurance company is happy to sell me an insurance policy for $20 a year. If I can cover $20 a year in insurance policy, I might be willing to do that to avoid those years where I'm paying hundreds or even $1,000 in earthquake losses, because the insurance company will help me out with that. But the insurance company will sell me the policy for more than the average annual loss, so that they're taking a profit on average over the long run. Okay, so that's some kind of loss calculations. We can start seeing how to integrate the hazard curve with these consequence models to get at metrics that are relevant for us in decision making and risk analysis.